Welcome, students, for this last chapter of General Chemistry 2. This chapter is Chapter 20, Nuclear Chemistry. Break this down into several different videos discussing the ins and outs of what goes on in a nuclear reaction in terms of atomic level. We're going to be looking at the kinetics of a nuclear reaction on a speed level, a decay, and then we'll be looking at eventually like the energy related to that on how much energy do nuclear reactions occur, and in the process we'll go into some of the science behind how nuclear reactors actually function to some extent. But before that, we have to go into the basics. So let's go ahead and get started. Now, unlike a chemical reaction, our nuclear reactions do not deal with the electrons, or very little of them deal with the electrons. Instead, they deal chiefly with the nucleus of atoms. Remember, the parts of the nucleus are the protons and the neutrons, collectively referred to as the nucleons. But in order to be able to do a lot of this stuff, we need to remember that the atomic number is equal to the proton count, and the mass number is equal to the sum of the protons and neutrons. And certain elements have isotopes, which means they have the same atomic number, same number of protons, but different mass number, different number of neutrons. So that will play a part in their stability. Now the basics. The idea here is that protons cannot just be stacked together willy-nilly. They are highly positively charged, and to stick them too close to each other would create a massive instability where they would fling each other away, repulsion. So neutrons are needed to stabilize most nuclei. That too many protons and the atom explodes, too many neutrons and it doesn't have enough kind of sticking power stick together, so it becomes too heavy, too unwieldy. But largely speaking, unstable nuclei will break apart, radiating particles until they magically become stable again, until they reach a number at which this is stable. This radioactive decay results in a nuclear changes. This is the only way to have elemental transmutation. It's the only way for one element to become another. Gases can become solids. Solids can become other solids. The only way to turn lead into gold is by nuclear chemistry. No amount of traditional electron chemistry can turn lead into gold, but only if we had atom smashers and could bombard lead with various atoms could we possibly cleave it and turn it into gold. But some elements have no stable isotopes, and these guys are always radioactive no matter what, while other elements simply have bad combinations of protons and neutrons that make them unstable, and these guys are radioisotopes. So radioactive isotopes. So like for example, carbon-12 and carbon-13 are stable. Carbon-14 is unstable, and as we'll see in a little bit, that 6 protons and 6 neutrons stable, 6 protons, 7 neutrons stable, 6 protons, 8 neutrons not stable. Now you've probably heard of the first 3 types of radioactive decay, but we'll introduce a few others. But the simplest one is an alpha decay. Alpha decay shoots out an alpha particle, which is essentially 2 protons and 2 neutrons. It has a charge of 2, a mass of 4 AMU. It's essentially like a helium 2 plus atom. Remember, this is not necessarily containing electrons, so it's not just a helium atom, but it has the mass, essentially the equivalent of a nucleus of a helium atom. So that alpha particle, it's heaviest, it's slowest, and has the least penetrative power. Most people's skin, the layers of dead skin, will block alpha particles. Now, beta particles, often referred to as beta minus, are the equivalent of high energy electrons. They don't have a mass, but they have a negative charge. They don't have a mass, they have a negative charge. These are a little bit faster, a little bit more penetrative, but can be blocked by most clothing or very thin layers of things. And gamma particles are essentially almost pure energy. They have no mass, they have no charge. You could think of them almost like X-rays. They are produced by various reactions, but they fly out and they are kind of hard to stop. They penetrate most things, but layers of lead work pretty well, or a decent amount of water. Like if you swum underground, if you had threw radioactive piece in the middle of a swimming pool, you would be safe on the surface. As you started to dive down and you got closer to the radioactive material, then you would become irradiated. But even on the surface of the swimming pool, you're probably still relatively safe. But so these are the basic ones that you most often hear about. The positrons is a little different. A positron, referred to as a beta positive, is kind of like a positive electron. So not a proton. It does not have a significant mass like a proton, but it does have a positive charge. So it's like flinging off a proton without the mass component. It's just the charge component of the proton. And another type of decay that can occur is electron capture. That while this is not a true decay where it flings something out, the electrons in the cloud get absorbed into the nucleus. So rather than flinging a particle out, an electron is absorbed and it creates a change. But during these radioactive types of reactions, there is going to be a parent nuclide, and this is going to undergo one or more of these types of decays, releasing various particles and producing a bunch of daughters. The parent will produce these daughters, and the daughters can then produce more daughters until we get to a stable atom. So, in general, here's a quick summary. So, alpha is helium 2 plus, essentially. 2 protons and neutrons are ejected. Example, radium undergoes alpha decay to produce radon 222. So it's lost 4 mass units, but 2 protons, and so it moves 2 elements to the left on the periodic table. Beta decay, often seen as an electron or B minus. Well, neutron breaks apart into a proton and beta. So a neutron, which is essentially, you could think of it like it's a neutral proton, but you could also think of it as a proton and an electron combined together to make a neutron. The proton has the mass and the charge. The electron has the opposing charge that makes it neutral, so it fragments apart. It turns a neutron into a proton. So the mass doesn't change, but the total number of protons do. So it flings, for iodine, for example, iodine-131 could fling off a beta particle and become xenon, still 131, but now 54. So it's moved one element to the right. Gamma decay is just excess energy. You're shaking off the energy as electrons start to relax. As the nuclei starts to relax. These often occur along with other types of decay. So, for example, cobalt undergoes a beta decay to form nickel, high energy, and some gamma particles. And that the high energy nickel then can gamma decay some more to form that lower energy nickel. Now, positron emissions. Instead of a neutron breaking into a proton, now a proton breaks into a neutron and gives off the positive charge. So the proton has lost its positivity, and so it reverts to a neutron. So carbon-11 could undergo positron emission to form boron-11. So this moves the element one element to the left. And electron capture, it's kind of also like positron emission. Electron is absorbed in the nucleus and it combines with a proton to make a neutron. So rubidium-81 could absorb an electron and become krypton-81. So it moves one element to the left, just like the positron emission did. Now some quick practice. So how do we go about doing this? Remember, everything must be balanced. Everything must be balanced. So, with that in mind, all of the charges, all of the masses on both sides must always work out. So I'm writing these down real quick. Francium 211 alpha. Okay. So, how do we do this? Really not hard. We need to figure out our atomic number. I have not given you the atomic number on each of these guys, so what do we go? We're going to go to the periodic table. Sodium is 11. Boron is 5. Iodine is 53. And francium is 87. So basically, we have an equation that says 24 and 11 is going to equal 0 and negative 1 and x and y. So 0 plus x has to equal 24. So what is the atomic mass that needs to be present in this atom? It needs to be 24. 11 on bottom, so this needs to be negative 1 plus y. Well, what number plus negative 1 would equal 11? That would be 12. So 24, 12. Element 12 is magnesium. So, of course, beta always moves it one to the right, so that is magnesium. The mass number is still 24, but so it's moved one element to the right. So this guy, boron, 8 and 5 equals 0, 1, x, and y. Well, 0 plus x equals 8, so whatever the element is, it's 8. 1 plus y is equal to 5, so this gets to be 4. Element 4 on the periodic table is what? Beryllium, I think? Yes, it is beryllium. So that is my product. Beryllium 8. This one we have 125, 53, plus 0, minus 1, and that equals x and y. Well, x is 125, and y, 53 minus 2, is 52. Element 52 is tellurium. Tellurium 52. I just looked what atomic number this is on the periodic table, and that told me everything I needed to know. This last one is probably the hardest one. 211, 87, 4 plus x, 2 plus y. So 4 plus x is 211. So that means we have 207, and 2 plus y is 87, so this is 85. So my element 85 with atomic number of 207, 85 is astatine, AT. So I'm just looking on the periodic table. You need a periodic table, but please use the numbers given. Don't use francium 223, because this is not francium 223. Don't use astatine 210, because this is not astatine 210. This is 207. The math wouldn't work otherwise. So you have to use the numbers given. But when you do it, it's simple math. Simple math, and then we're turning that into elements. Okay. Now, with that in mind, radioactive series. Most radioactive decay does not just go through one decay. She goes through a series of decays. That essentially, in a radioactive series, a radioactive nuclide will undergo a series of alpha, beta, and sometimes gamma decays until it reaches a stable nuclide. So uranium, for example, uranium-238, the most common form of uranium, undergoes an alpha decay, and then 2 betas, and that puts it at uranium-234, and then that uranium undergoes 1, 2, 3, 4, 5 alpha decays, not in quick succession, but in a row, and then it can undergo, no matter what, it undergoes at least 1 beta decay, but then it could either alpha decay from there, or beta decay again, and then alpha decay from there, and then it undergoes enough beta decays to put it at 21084, which is polonium, 21084 polonium, and then undergoes one last alpha decay to form lead-206. Now, this is not the most common form of lead, but this lead only comes from uranium-238, and so this process is the only way to form lead-206. But once it gets there, it is stable and will not decay anymore. With that in mind, we measure this radioactivity as in disintegrations, and that how many particles are emitted per second, and that is referred to as the activity. We can measure activity units in becquerels, which is just a term for disintegrations per second, or in curies, which modifies it becquerel, I think, based on, radium, which is one of the things, and based on the activity of radium, which is one of the elements that Marie Curie and her husband worked very strongly with. But so Becquerel is also a radioactive scientist that was working with us. But so how does the detectors actually work? Essentially, they have a little wand that has a little shield on it that blocks any species from just coming in. It's an enclosed gas in this little wand. Now, the radiation can penetrate that gas just fine, and when it penetrates that the screen and goes into the wand, it ionizes the gas, and the gas can then fling themselves to a positively charged central wire, and it essentially the protons go to the walls, and the electrons go to the wire, and it can essentially conducts electricity, and so it picks up this as electric zap, and it can measure how much ionizing radiation the thing is generating. Now, with that in mind, how do we predict radiation? That normally protons, as I said, would repel each other, but there is a strong nuclear force between protons and neutrons that hold the nucleus together. That these guys will pack in certain ways, and this will generate there's a certain magic numbers that work its way out, that they can pack in certain ways and be very stable. Atoms with between 2 and 20, atomic number 2 and 20, tend to have equal numbers of neutrons and protons. Atom 1 doesn't need a neutron because one proton can't really repel itself. But all the other elements, helium and lithium, tend to, essentially the atomic mass is double that of the atomic number, because they tend to have equal number of neutrons. But as you start to get more and more and more protons above atom 20, you start to need more neutrons to stabilize it. And so, and once we get to lead 82, lead is the heaviest known stable element, that it has a stable structure that is not necessarily radioactive. Every element past lead is at least mildly radioactive, that it will not hang around forever. Now, does that mean it will disintegrate immediately? No. A lot of things have radioactive decays in the millions and billions and trillions of years. Uranium was generated long time ago when the sun exploded and Earth was generated. If it was a fast radioactive decay, we would not have any uranium in the Earth. But clearly we do, and that's what we see. But a lot of it is also decayed. But so there's essentially a belt of stability, looking at the ratio of protons to neutrons. That every of those blue dots are a stable nuclide, stable ratio of protons to neutrons. So if we go above that belt into the green area, we have essentially too many neutrons. And so it's going to undergo a beta decay, which turns a neutron into a proton. So it moves diagonal right down to get back towards that safety belt. When it's below the belt, it means we have too many protons and not enough neutrons. And so it needs to either undergo beta positron emission or electron capture. When it undergoes those, it converts a proton into a neutron, and so it moves diagonal up left to get back to the belt. And everything above lead in that brownish yellow region are just alpha emitters, and then they're just too heavy altogether, and so they give off two protons, two neutrons, and they're essentially moving diagonal down left to try to get us back to that belt, back to some sort of region of stability where it can move upper left or lower right to get back to that belt. now, and that's basically what I said. So above the belt, when we have too many neutrons, we break the neutrons and form protons. Below the belt, too many protons, the other way. And then here's the one thing I didn't mention. The lighter nuclei, because they don't have a lot of electrons in the first place, tend to undergo positron emission. While heavier nuclei, because they have more electrons and a bunch of electron clouds, prefer to go through electron capture, that the electrons in the cloud can decay into the nucleus. But yeah, and then everything above that cloud, above that belt, will go through alpha decay. But that is where I'm going to leave you for today. In the next video, we're going to start to discuss the decay process and looking at the kinetics behind that decay. In the meantime, have a good day.